Good morning, one and all. Today's topic is Bootstrap Loader. Before we see about the Bootstrap Loader in detail, I want you to analyze this architecture of a computer device. So in this, you can look here where there is something like ROM, a read-only memory. This is the main memory part, and here is the flash memory, or you can say that hard disk, and this is what the processor part, including the registers. Now the point is that here is the very important a piece of your computer, which is the operating system. As such, as soon as you switch on your device or as soon as you restart your device, you feel that at the beginning itself what will be working, in the sense it is nothing else than, or it is none other than the operating system. So as soon as if you want this computer to operate perfectly or work properly, then your operating system has to be executed. It can be either operating system or it can be any other application software. If you want to execute any software, including operating system or any application software, those operating system or those softwares must be loaded to the main memory. So remember, any application software or it can be any system software, if you want to run it, so it must be available in the main memory, then only those can be executed. Now the point is, in the same way, even the operating system must also be loaded to the main memory, then only it will get executed. So as soon as the operating system is executing, in the sense it means to say that you can work with your system, or in the other way say that system is working. So in the other means, you say it as if the operating system is loaded to the main memory or stored to the main memory, then it will execute. If it executes, then only you can work with your computer, or your computer can start working. Now here is the point, that who will load this operating system to the main memory and at what time. It is, you call it as a booting time. So as soon as you switch on your device, there will be at the beginning process, which you call as a booting process, a boot process. That boot process, which is the function where what is happening at the time, it is what you will be loading the operating system into the main memory. But who will do that? That is what will be taken care by the Bootstrap loader. In turn, what is this Bootstrap loader? It is a kind of firmware. So it is a kind of firmware which will be available in the ROM, read-only memory, which will not be erased even if you switch off this device, because you might have studied something like main memory, which is the volatile memory. As soon as you shut down, definitely as soon as you shut down or as soon as you restart, definitely the memory space or memory contained in this, or a data available in this main memory, will be erased or deleted. But here we are dealing with the Bootstrap loader, which will be available in the ROM, which is on the read-only memory, so it will be a permanent. Now what is the functionality of this Bootstrap loader? As soon as you switch on, the booting will start, a boot process will start. What will happen at that time, in the sense, this is the one which is the Bootstrap loader, is the one which will load the operating system, from where? From the hard disk, or you say that flash memory, from this hard disk or flash memory to this main memory. So this Bootstrap loader, which is available in the ROM, which will load this operating system into the main memory. But the point is that, however you say anything for that matter, if it has to be executed, in the sense it must be loaded to the main memory. You may get the question like, don't we load this Bootstrap loader to the main memory? In the sense, yes, it is yes. So in detail, if you want to understand, as soon as you switch on your device, first thing which will load it to the main memory is not even operating system, it is the Bootstrap loader. Bootstrap loader will occupy into the main memory starting from the address 0. That is what at the beginning. From the beginning of main memory, what will be occupied? It is the Bootstrap loader. Once the Bootstrap loader is occupied in the main memory from the beginning, then it will start executing, which Bootstrap loader is getting executed. But what is its functionality? Its functionality is to fetch the operating system from the hard disk device to the memory. That is what the functionality of your Bootstrap loader. So here, as a highlighting part, remember, as soon as you switch on your device, this Bootstrap loader from the ROM, it will occupy the main memory. Then it will fetch the operating system from the hard disk into the main memory. Once this operating system is loaded to the main memory, then your operating system can work properly. If the operating system can work properly, then only you feel that my device is working properly, or my device is ready for the execution. So it is something like that. Now here we say that it will be loaded to the main memory. Who will load the operating system to the main memory? It is the Bootstrap loader. So Bootstrap loader is the functionality of the Bootstrap loader is to load the operating system into the main memory. But the point is that from which address it will start loading, in the sense with respect to SIC bar XC machine architecture. With respect to SIC bar XC machine architecture, remember it will always start loading from the 80. It is the hexadecimal address 80. So from here the operating system. So in this diagram, it is very clear that you can understand. This is what the main memory. In the main memory, what will be occupied from the address 0? It is nothing else than the Bootstrap loader. Bootstrap loader itself or himself will occupy from the address 0, and then from the address 80 onwards it will start loading the operating system. From where it will fetch? From the hard disk device, where the input port is F1, which is the input port. So from the either you say the flash memory or a hard disk memory, so it will fetch the operating system, or in the other means to say that the character object codes belongs to the operating system will be fetched from this F1 and will be loaded to the main memory. From where it will be loaded? Remember, it will be loaded from the 80 itself in case of SIC bar XC machine architecture. So I repeat, so as soon as you switch on your device, what will happen in the sense, Bootstrap loader will get the object code of the operating system from the F1, which is the hard disk or is a flash memory, and stored into the main memory. And where it will be stored? It will be stored from the address 80 itself. That is the functionality of Bootstrap loader. Now this is where we are just demonstrating here. So Bootstrap loader, what it will do, it loads the first program whenever you run your computer, and that first program, which is nothing else than the operating system. And where it will be loaded? It will be loaded from the 80. Why not it is from 0? Because Bootstrap itself, it will be stored at the address 0. So operating system will be loaded from the address 80. And the final point I want you to be clear here, Bootstrap loader is also considered as an absolute loader. I hope you understood the concept of absolute loader from the past previous one, my previous presentation on the absolute loader, because which never changes the address every time. When the address will never change every time, object codes will never vary. Here also I am talking about the address in the main memory. It is always, any number of times you switch on your device, any number of times you restart your device, the object code of the operating system will be loaded to the main memory starting from the 80 itself, not anywhere else. So as it is fixed, the starting address is fixed, so the operating system will never vary with the address. So only this Bootstrap loader is a kind of your absolute loader. So your Bootstrap loader is a kind of absolute loader. And right now we are dealing with the SIC bar XC machine architecture. So only it is started loading from the address 18. Now what will happen here? However, I said first you need to keep fetching the characters from the F1 device, and convert them into the hexadecimal values, and then keep loading to the memory starting from the address 80. So that is what so here is the complete process. You can see, so X is initialized to 80 because you need to start loading from the address 80. And whenever you talk about the ASCII codes of any character, so it is definitely like, for every character you have the ASCII code. Based on that ASCII code itself, every time you generate the 1 byte number, and that 1 byte value will be loaded to the main memory. So for that process itself, here you understand, you get the 2 characters. So from this get C, which is to get the character, and that will load it to the accumulator. As soon as you get it, that will be pushing to the other register, which is S. Because in case of SIC bar XC, we have the plenty of registers like AXL, BSTF, PC and SW. So as soon as you read any character from the F1 device, that will be loaded to the A, and that you are pushing to the S. Then again you are trying to read the next character, and you combine both, you combine both, that combined data will be stored to the main memory wherever it is pointed by x, and again you will also usually increment the value of x to point to the next location. Now let's see what does this happening in this getC, because this getC which itself it is acting as a separate procedure or a function here. What is happening here in the sense, we are just checking whether the character whatever you read from the input device, which is f1, from the input device whatever you read the f1, that character we first will check whether is it a 04 character. What is this 04 character in the sense, this is the end of text character, because 4 is the hexadecimal or the decimal value for the ASCII EOT, which is end of text. Here you can observe this is what end of text, where this is what the end of text, or you say end of transmission. This is the end of transmission. So as the number, the hexadecimal or the decimal value related to the ASCII character end of transmission is 4. So we need to make sure that is it the end of the transmission or not. If it is the end of transmission, definitely you need to jump back to the address 80 for starting the execution. If not, you need to process such a way that making sure that if it is less than 48. Why do we check it is less than 48 in the sense this, because that 48 is the decimal equivalent of your number 0. See, you remember any character you are reading from this input device, it can be, or will be considering the number such a way that from 0 to 9 and A to F, because of for the hexadecimal equivalent. So we'll be considering from 0 to 9 and the A to F only. So if that is the case, what will happen in the sense, whenever you read this particular character, suppose if you read 6, the decimal equivalent of it is 54. When you read E, the decimal equivalent of E it is 69. So based on those values, you will be comparing with the 48. If the value is already less than 48, so it means to say that when the value will be less than 48, if it is less than 48, it belongs to any special symbols like this. It is not belongs to our numbers. In such case, you need to violate them. You need to neglect them. So if it is not, then only you will be subtracting by 48 value to make sure that it is in the range of this 0 to 9, which is from 48 to 57. If it is more than this, you subtract again by 7. You see here, you will subtract again by 7 more. You subtract by 7 more for the purpose of this A to F. For the purpose of this A to F, you subtract by 7 more. So that is what the simple algorithm we have here. So what happens? So let me put it in a simple such a way that you need to read 2 characters at a time. First, it is something like this. You call this getC for reading the first character. You come here, you read the first character and make sure that is not the end of transmission, and also it is not less than 48, and whatever the character you read, that will return back. That whatever resultant which is written here, you push it to the one more register, yes. One more register, yes. Then you read the next character, because we will be calling the getC again. You read the next character from the getC and combine both, which will form a complete 8 bits, because earlier 4 bits which are there in the yes register, now you read whatever you read. When you combine, it will create one complete byte. It will create one complete byte that you are going to store into the X. So let me elaborate even more. Before that, remember the decimal equivalent of 0 it is 48, decimal equivalent of 1 it is 49, and keep going till decimal equivalent of 9 is 57, and decimal equivalent of A it is 65, decimal equivalent of F it is 70. These numbers keep in mind. See, now here is my algorithm. So this itself, let me elaborate such a way that, so here at the beginning, my boot process is beginning at the 0, because already I said your bootloader itself is loaded at the 0, whereas your operating system will be loaded from the 80 onwards. So only you are initializing the X value with the 128. What is 128? 128 is the decimal equivalent of your hexadecimal 80. I hope you know that addresses will be represented or considered in the form of hexadecimal. So 80 is the hexadecimal value, decimal equivalent of that 88 is 128. So I am initializing X with the 128. Then what I am doing, I am jumping to the getC, because when you jump, that's what jump to the subroutine getC. So come here, come to this getC. In this getC, I need to read the character. Before I read the character, I allow to check this input device. So that is what test device. Test device, input device. What is input device? Input device is nothing else. Here it is my F1. So test that input device. I hope you know that if that input device is set as flag is set as equals, then the device is not ready for reading. So you need to jump back to this and keep checking, keep testing. Once this input device flag is set as less than symbol, then only I can read the character. I can read the character from the input device. But remember, I hope you know that as soon as you read the character, default it will be loaded to the accumulator register. That accumulator register content I am comparing with the 4. Why I am comparing with the 4? Because I already said 4 is the equivalent of your end of transmission. I just make sure that is it the end of the transmission, or are there any more characters? If it is end of the characters, what I supposed to do? I just need to jump to the location 80 for the starting for the execution. So if the character is 4, I just need to jump to the 80 address 80 for starting the execution. If it is not 4, if it is something else, then I will be comparing with the 48. Why I will be comparing with the 48? To make sure that is it the number which is less than this, or a character what you read, is it less, it is none other than this numbers or not. See, like this, if it is less than 48, it will be anything related to these special characters which we are not going to consider. So that is the reason you will be comparing with 48. If it is less than, you neglect that character, or the skip that character which are less than 0 numbers, and go back to the get C again, try to read the next character. When it is the decimal equivalent of that particular character is less than 48, then it will be any character other than these zeros. That's what less than zeros, which are special symbols. We do not want to consider these, so we are going to skip that and again jump back to the get C for reading the next character. If it is not less than 48, if it can be equal or greater than 48, if it is equal or greater than 48, then what are you supposed to do? You will be subtracting with this 48 value. When you subtract this 48 value, if the resultant is less than 10, that is what, 0 to 9. If the resultant is 0 to 9, then that 0 to 9 itself will be returning it as a result. Because if you compare once after you subtract by 48, you are comparing with the 10. Is it less than? If it is less than, you directly go for this return loop, where you will be returning from the subroutine. If it is equals or greater than 10, you will be subtracting by 7 more again. Why do we subtract this 7 more again? In the sense, any resultant value, if it once after you subtract this by 48, resultant value should be between 0 to 9. It should be between 0 to 9. If it is 10 or more than 10, you subtract by 7. Why do you subtract by 7? In the sense, to get this ASCII values. To get the hexadecimal equivalent of this ASCII values, which is A to F. So for that reason, so that is why I already said you need to know about this 0 to 9 and A to F decimal equivalents. So if it is greater than, even after you subtract by 48, even after you subtract by 48, if the resultant value is still 10 or more than 10, you subtract by 7 more again to make it as the characters between A to F. So like that. So whatever the character you read, what you did, you first check the input device whether the device is ready or not. If it is ready, read the character, compared with the 4. Why do we compare with the 4? It is for the end of the file or end of the transmission. If it is end of the transmission, so directly you jump to the address 80 for starting the execution. If not, compare with 48. If it is less than 48, it means to say that the character which is less than 0 and those special symbols we are not going to consider. So skip it and go for the reading the next characters. If not, if it is not less than 48, it can be equals or greater than 48. In such case, subtract by 48 value. When you subtract by 48, the resultant can be anything. If the resultant is again 0 to 9, if the resultant is 0 to 9, directly you jump to this return and return that resultant value. If not, you subtract by 7 more again, and resultant you will be giving back to this main routine. And what will happen in this main routine? You see, as soon as your resultant you get the resultant, that which is loaded default, it is present in the accumulator, that will be pushing from accumulator to the S register by using this RF, which is register move. So you will push the content of accumulator to the S, and once after you push it, again you do the shift left by 4 times. Very importantly, you do the shift left by 4 times. So remember why it is 4 bytes in the sense. So any number you can consider from 0 to 9 and A to F. So 0 to 9 and A to F, all these will need only 4 bits of memory space, because 0 is 4 zeros. 1 is 0001, 2 is 0010, 3 is 0033, like that. 9 is what? 1001. Whatever A, 1010, whatever F, it is 4 ones. So like that, in order to fit this 0 to F, you need only 4 bits. So just skip by 4 bits. That's what, shift by 4 bits, and you will be shifting to the left side. You will be shifting to the left side. Then once after that content of the yes is shifted by left side, again you are jump into the get C again. That's what you will be calling the get C subroutine again, to read the next digit or to read the next character. So again jump to the get C again, as usual. Check with the input device if it is ready or not. If it is not ready, keep checking. If it is ready, read that character, read that number. If that character what you read, if it is less equal to the 4, so then jump to the 80 for starting the execution. If not, compare with the 48 just to make sure that is it less than 0 values or not. If it is less than 0 values, you need to skip that. If it is not less than 0 values, again subtract by 48. If the resultant is, if it is between 0 to 9, you return that resultant. If it is not between 0 to 9, again skip, again subtract by 7, and that you return. You see whatever the resultant now you return, that is here, and again as usual it will be in the accumulator register. So earlier what was there in the yes and what is there in the current A, both you will be adding by using this add R. So content of yes will be added to the content of your A. So now the resultant complete 1 byte value, the 1 byte value which is available in the A, that you are going to store to the memory, wherever it is pointed by X. It is just like stch buffer comma X, but here it is not buffer, because it is not the buffer space, it is the main memory space which has started from the 0, but where you are loading, where you will be loading at the place wherever it is pointed by X. So that is why it is 0 comma X, stch 0 comma X. In the main memory, wherever it is pointed by X, that is where you will be loading this 1 byte character. Once after you are done with this storing this 1 byte character to the main memory by using stch 0 comma X, then as usual you will increment the value of X. And again jump to this loop for reading the further characters. So like this it will be keep continuing till when? Until you get the end of file. Once you get the end of the file, this is where the JEQ80, this is where this process will be stopped, or a break to this process, and jump to the 80 for starting with the execution. This is the break for this complete process. I hope you understand. So let me take up a simple example. So understand, this is not the constant one, I am just taking an example. Remember, I am just taking an example. This is not the object code of, I am considering that this is the object code of your characters of your operating system, but this is not the actual one. I am just taking an example. Suppose this is the input series. And at the beginning, as usual, you started with the 0, but you initialize the X with the 80, the address 80, or you can say that. So when you say that 80, so suppose it is 80 is nothing else, the decimal equivalent is 128. So again you are calling what? Get C. As soon as you call get C, it will come here. You tested the input device. Which input device? It is the F1, and I hope it is ready. If it is ready, you read that character. So what is the first number? It is the 2. So as soon as you read this 2, so you understand this is the 2 which you read, but the decimal equivalent of that 2, it is 50. Decimal equivalent of the 2, it is 50. That 50 is compared with the 4. Is it both are same? If you have both are same, you could have jumped to the 80 for starting the execution, but this 50 is not equal to 4, so this condition fails. Again come here, compare with the 48. Is it less than 50? Is it less than 48? No. If it is less than 48, you could have skipped that character and start reading the next character. Now the 48 is not, when you compare with the 48, 50 is not less than 48, so this condition also fails. So come to this, when you subtract by 48, so when you subtract 50 minus 48, what is the resultant? It is 2. Again you are checking whether the 2 is between the 0 to 9. Obviously yes. When it is yes, so you don't have to perform this subtract by 7. So you will directly, what you do, you go to this return and return subroutine. What you are returning right now? Remember what you are returning right now, it is the value 2. When you return this value 2, that will be loaded that will come here. So what that is nothing as the content of your accumulator register, because the return data will be defaultly will be in the accumulator. So how do you represent this 2? Here if you can see, that is what 4 zeros I write as 0010. That is what the representation of 2. Then what I am doing, I am just pushing that content through the yes. I am pushing the content of your accumulator to the yes. So I am pushed to this. So the content of A is pushed to the yes. Again what I am doing, I am shifting the bits by 4 to the left side. So when you shift this content left by 4, so this 0010 will come here, and this will be empty, which are loaded with the zeros. So now what is the content of yes? It is what you can observe this 2 and null. This is what 2 and null. Again you are calling what? You are calling the get C. You are jumping to the get C again. Again come here and read the next value. Next value is what? 7. Next value is 7. Read that 7. Again compare. What is the decimal equivalent of 7? It is the 55. You can also make it out from this. You see here the decimal equivalent of 7 is what? 55. So decimal equivalent of 7 is 55. That you compared with the 4. So both are not same. Again check with the 48. Whether the 55 is less than 48? No. Again subtract by 48. So when you subtract 55 minus 48, the resultant is 7. Resultant is 7. Again check it. 7 is it less than 10? Obviously it is in the range between 0 and the 9. So it is less than 10. So you don't have to subtract again. So what is the value returned? It is the 7. What is the value returned? It is the 7. So when the value it is returned is 7, so that will go back. So this 7 will be returned back. Yeah, so that value 7 will be returned back. So when the 7 is returned back, which is the value of your A. This is the value of A. So how do you write 7? It is what? 4 zeros followed by 0 and 777. This is the 7. What you are doing again? Add R S comma A. What was the content of yes? It was this. This content and this content both are added. When you add, see, you can see this 0 plus 1 1, 0 plus 1 1, 0 plus 1 1. So like this, what is the resultant you get? You are getting, it is what? This is what final content of your A, which is 2 and 7. 2 and 7 completely makes as a 1 byte. 2 and 7 makes one complete byte that will be loaded to the main memory wherever it is pointed by your X. Then you increment the X. So now when you increment the x by 1, it will become, earlier it was 80, now it will, as you are incrementing for the first time, it will become 81. So it will become 81. Then again you go back to the loop. Again let me take up one more trace. Go back to the loop. When again you are calling the get C. When you call the get C, now the next character is what? 4. You read that 4. What is the decimal equivalent of 4? It is the 52. Again compare with the 4. Is it equal to 4? No. So again, is it less than 48? No. So then subtract by 48. When you subtract by 52 minus 48, you will get 4. Is it less than 10? No. So return 4. When you return 4, this is the content of your A, which is 400100, which is the 4. Again shift left by, so that you will be pushing to the yes. Again shift left by 4. So you will get this 0100 and 4 zeros, which is the content of your yes. Then again you are calling the get C. When you call this get C again come here, read the next character. What is the next character? It is what? D. So sorry, this is not the 4, it is the D. Decimal equivalent of D is 64. You can make an observation on this. So decimal equivalent of D, it is 68. So this is not the 4, sorry for this is the D. So decimal equivalent of your D is 68. So that 68, from the 68, I hope 68, yeah, decimal equivalent of D is 68. Yeah, that you again compare with the 4, so it is not equal. Again compare with the 48, is not less than. Again subtract by 48. When you subtract by 48, there is, for 68 minus 48 is what? 20. So again you compare with the 10. Obviously 20 is greater than 10. So what are you supposed to do? You need to subtract by 7 more. When you subtract by 7 more, so 20 minus 7, what is the resultant? It is the 13. It is what? 13. So return that 13. But how do you write 13? This is what the return 13. This is 1101. 1101 is what? 13. Again as usual, add R S comma A. So content of yes and the content of A both are added. So this is the resultant. What is the resultant you are getting? Which is 4 and 13. 30 is nothing as D. So this is makes one complete byte which will be loaded to the main memory. So like this, every time you keep loading, you keep fetching the two numbers at a time. So this is what the first number, this is the second number. Before you get the second number, you push the second number to the other register and also shift left by 4 times only. The reason why you will be doing shift left by 4 times, any hexadecimal number between 0 to F which requires only 4 bits, it can be from 4 zeros to 4 ones, which is F. So only you will be shifting by 4 bits. Then again get the next number, and that next number and the previous number, when you concatenate, and you say when you add both, that is by when you add both, you will get one complete byte, you will get one complete byte character. That is the one which will be loaded to the main memory, and this is the process which will be continued further. I hope you understand the process of your Bootstrap loader. Again, let me go back. So Bootstrap loader is nothing else. You get the object code from the F1 device. Object code of what? It is the operating system, and loaded to the where? Loaded to the main memory. So that is the process of your Bootstrap loader, and where it will be loaded? It will be loaded from the address 80 itself, nowhere else. So every time it will be loaded from the same address only. It is what? Absolute. There is no changes in the starting address. There is no changes in the starting address 80. So only Bootstrap loader can be considered as absolute address. So from which device it will be fetching? From the F1, and every time you will be fetching and will be keep loading from the starting address 80. And this is what a simple pseudocode I record as algorithm, and this is the ASCII table, and this is the complete you can say program of your Bootstrap loader for the SSC bar XC machine architecture. Thank you.